What's up guys, today I'm going to be simulating a rover using ROS2 and Gazebo. Basically I'm going to code up a file that'll actually tell the computer what my robot looks like, and then I'm going to put it into a simulation and drive it around, and at the end I'll actually put it into an actual model of the lunar terrain. So let's get into it. So before we can simulate robots with ROS, we need to know what ROS actually is. So ROS stands for Robot Operating System, and it's basically a framework for building robots. ROS is built up of nodes and topics. A node is a program. You can program it to do anything you want, motor control, user input, simulations, anything. And topics are a way for nodes to communicate with each other. Now, they can do this by either publishing messages to topics or subscribing to messages from topics. Now, for actually simulating a robot, we're going to use something called transforms. Now, a transform is just like a transformation in math class, where it's instructions on how to get from point A to point B. But in the case of ROS, we call them links and joints. So to actually simulate and visualize a robot, we're going to write a URDF file which contains all the information about a robot, and that information is going to get passed on to the robot description topic. Now, there's a node called Robot State Publisher, which is built into ROS, which will take in the robot description and publish transform data to the TF topic. It'll also take in information from the joint states topic, which just holds information about the rotation and position of certain joints if they are able to move around, which in our case will be the wheels of our robot. There's a software called RViz, which helps you visualize robots, and it'll take data from the transform topic. There's also another software we're using called Gazebo, which is a physics simulation. So that physics simulation is going to be calculating the new position of our rover and updating it in the joint states topic, which will eventually be visualized in RViz. So now that we know how ROS works and what we're doing, I'm going to code up our URDF file, visualize it, and then we're going to simulate it in Gazebo. This is kind of where we're at right now. There's basically nothing. So this right here is a URDF file. Now, URDF stands for Universal Robot Description Format, I believe. And a URDF file is essentially made up of joints and links. Now, each link is basically a point in space, and each joint connects different links. And you can use these links and joints to build a model of a robot. You can build the description of a robot. Now, what I've just done is write up this launch file, which essentially, it grabs the URDF file I have over there, and it runs it through this built-in ROS node called Robot State Publisher. Now, Robot State Publisher is the node that will actually send it'll convert my URDF file into ROS transforms, which can then be used by RViz to display my robot. All you gotta know is that when I run my launch file, it says got segment base link, which is exactly the name of my link in the URDF file, which is step 1 to simulating a robot. I've changed up the Rover URDF a bit. We're actually routing over to another file called Robot Core. And so far, all I've done is I just established some colors that I want to use for the rover. And we have one link, a joint, and another link. So this is the base link, same as before. We have a joint called the chassis joint, which is connecting the base link as the parent to the chassis. And then we have a link called the chassis, which has a visual, which will be a box. So hopefully, when I go ahead and run this, it should find, there we go. It found the base link and it found the chassis. So now what we can do is we can open up another terminal and go ahead and run RViz. There we go. So we can actually see the chassis and the base link over here in RViz. Now we can actually see, oh my gosh, the chassis of my robot. And actually, I believe this is on the wrong side. Yeah, I believe this is on the wrong side. So let me go ahead and fix that really quickly. I think the issue is that over here, the joint here, this should actually be in the negative X direction. We can leave that running, but if we go over here, we close that out and we run it again, and we open up RViz, we'll see it moved, and now the chassis is actually behind the base link. So that's pretty cool. It's the base of our robot. If I go to the chassis and I change the material color to, say, blue, it doesn't update immediately. I do need to rerun the launch file. But when I do, the color changes. Nice, 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 nice. Then we have a nice little, that's nice. Yeah, that's about what I expected. And then if we go here, we can rotate each individual joint. Nice, okay, sick. So let me just do the same for the back two wheels now. Open up RViz and hopefully, okay. Oh, it's not right. That's not right. Oh, there we go. So I coded up a launch file that basically runs Robot State Publisher, starts up a Gazebo simulation, and spawns my rover into the simulation. So if we run it, we'll see a bunch of stuff happen in the terminal. You can see it got all the links and joints from our robot. It's spawning in the entity, and now we see Gazebo, and we have our robot here. So now that we have this, we can actually go ahead and run RViz. All right, so we have our robot here. So Now I'm going to open up one more terminal. So now we have a terminal that's actually taking input from my keyboard. So if I press a button, we'll start to see the robot move. So here in Gazebo, we can see our robot moving. And in RViz, we can actually see the wheels rotating on the robot. So if I hit a button, this should increase the speed. Hopefully it'll go a little faster, which we can see. And that's pretty cool. And I can stop it and actually have it rotate. And it kind of rotates like a little crazy, but now we can have it go in any direction. And we can also stop it and have it go backwards as well. So that's not the limit of what we can do with Gazebo. We can actually, within Gazebo itself, it has built-in models which we can bring into the simulation. And right here, this is the one I want, Apollo 15 landing site height map. So if I double click that and bring it here and click, it'll hopefully, oh, we saw the robot move, so it's loading it all in right now. There we go. So we should be able to actually see our rover. We're simulating our rover moving around lunar terrain while also being able to see the position of every single joint in the robot. So Gazebo is a physics simulation and it has all the information about the robot, its position, and the world around it. But RViz is basically what the robot sees. So right now the robot only knows what its own position is and what the orientation of the wheels are. If we added a camera to our simulation, within RViz we would actually be able to see what the world around it looked like. And if we added a LiDAR camera, the same thing would happen. We could actually see the point cloud being generated. But for now, this is good enough. We can simulate our robot, and this is pretty cool. So when I have a real physical rover, we're going to be using RViz, but we're not actually going to be using Gazebo because we don't need a simulation if our rover is in real life. That means real life is basically going to be the simulation, and all the data, the joint data, is going to be grabbed from our physical motors that are on our rover. Thanks for watching, guys. If you thought that was cool, then definitely make sure to subscribe. I've actually already started building the physical version of this rover, so hopefully we'll get a video out about that soon. If you're impatient, you can always go check out my TikTok and Instagram at ion.studies, where I'm already posting little snippets of the physical version of the rover. Bye.